Hey, so just wanted to show the other aspect of this Z80 board that I developed, which I already showed you, like front panel controls. You can interact with this thing. You can examine memory locations, examine next. You can deposit values, deposit next. You can single step and so on and so forth. But it's also got a command line interface. So I'm using a USB cable connected to my laptop right now, and I'm charging it in the process. So my charge light is on. When it's fully charged, it'll switch to done. But I also have the ability to communicate with this through whatever my favorite serial interface is. So this thing shows up as a USB device. It's a FIDI 231. So drivers for that are plentiful, and under Windows this shows up as a COM port. And so you can take your favorite serial I/O program. I'm going to use TIO and just TIO to this device, and it resets when it gets a connection, and my window here is saying ready. So I'm at a command line prompt, and I can type any of a number of commands to interact with this this development board. So, for example, I can say examine the contents of memory location 0, and it'll show me location 0 has the byte DB. And my address bus, has changed to all zeros, and my data bus is showing a D followed by a B. And I'm going to ratchet down the intensity here so that the LEDs don't flood each other out. So I can examine successive locations by just saying E. So that'll show me the next location. That's location 1 is an FF. And anytime you hit enter, it repeats the previous command. So I can start stepping through memory just by hitting enter. There's location 2 is 47, location 3 is a 3E, and so on. I can go back to location 0, and I could say let's deposit a 55 in there. And now location 0 has a 55. If I go back and examine 0, there's a 55 on my console window, and it's also showing me a 55 on the display. Of course, I can come in here and I can say, examine next and step through my locations like that. I can put in an address of 0 and say examine that, and there's a 55. If I examine address 100, that's got some different value. It's got a 0. If I examine next, location 101 looks like it has a C, B stored in it. And if I say examine 101, there's my CB. Right? So these things are linked together now. Now normally, there's a Z80 processor and there's a 64K static RAM, and those two chips talk to one another directly. And when the Z80 makes a memory request, the RAM responds, and so on. And the processor inside here, the AT328P, stands aside and lets interactions happen between the Z80 and the memory, and it doesn't take part in those. The clocking is coming from a 4 megahertz oscillator on the board, but when you're in this mode, when the system is not running, right? So if I hit the run button, then the system is free running. But if I hit stop so that it's actually stopped, then there's this AT328P processor inside that takes over and has the ability to monitor and manipulate the Z80. And through the Z80, the contents of the static RAM. So in this case, I can examine memory, I can deposit values, I can say dump, and let's say dump the contents of memory from location 0 through 1FF, and I get, my favorite hex style dump. Bunch of zeros in there right now, right? That's just kind of coincidence, but I could go down to examine location 0. And I don't know, I could start depositing some values in there, and I can just fill the first few locations with that value. And now if I dump locations 0 through 20, right, I can see I've loaded in a bunch of 28s. But a lot of zeros in there, which is kind of surprising. Anyway, so we can do various commands here. We can start the machine running, so I can say run, and now it's in free run mode. And you can tell that because this clock light is constantly illuminated. If I stop, that clock light goes off, that rightmost bit. And from the front panel, if I hit run, that light turns on saying it's running, and if I hit stop, it'll turn off. Right? So the command line interface gives you, first off, a number of ways to do the things you would do from the front panel, but by typing them in, you know, or feeding them in from a input file, perhaps. What else can we do? So we can step the process. So let's go back to location 0 and we can start stepping. So every time I hit an S, it will move forward one memory cycle. So right now it's in an M1 cycle. It's doing a memory read. Now it's doing a memory request read, but it's not an M1 cycle. So it's fetching something like an operand. And now it's back to an M1 cycle. I can do a T, which ticks me a single clock tick. So right now I'm doing a opcode fetch. Now I'm in some intermediate state, right? This is a state in between the opcode fetch and the next part of that instruction. There's a memory request, but there's no read or write. So that may have been a memory refresh. And now I'm in a quiescent state. And now I'm doing a memory read, reading an operand. And I'm still reading the operand. And now I'm about to go back into M1. I've got my M1 flag asserted. And in the next clock tick, the memory read and memory request lines will go active. So you can step through one clock tick at a time like this. You can also do this from the front panel, right? Remember, if you hold the step button for a long press, it will switch to M1 cycle at a time mode. If you hold this for a long press again, it will switch to single tick mode, where it's just ticking through one clock tick at a time. I can also do M1 cycle at a time mode with an uppercase S, and that will go from one M1 cycle to the next, which in this case is not very interesting because we're doing no ops. All right, what else do we have here? So we can examine memory using an E. We can examine the next location. We can also disassemble. So I can say I, and it will disassemble the instruction at the current location. And if I say I again, it will disassemble the next instruction. I loaded in a bunch of 28s. Those were jump relative zeros. So I can say I and put in a number, and it will disassemble that many instructions. So a way to interpret your code without having to pull out your Z80 quick reference. We can deposit data. So I can deposit, you know, a 45, a 56, deposit a 77, deposit a 12 a few times, and deposit a 23. So I put some random stuff into my memory, and if I look at those as instructions, I can see what those instructions look like. Alright, we also have the ability to monitor the buses while the system is running. So, well, let me show you something else first. We have a flash memory in here, remember. We can read from or write to that flash to save or restore the contents of the static RAM. So I've already preloaded one of the file registers on that flash memory. File register 1 has a short loop that basically counts. And so I'm going to load that program into RAM. And so that's the read command. So I'm going to read from file register 1, starting from page 0 and ending with page 1. And we'll get some activity here and a monitor on the screen, and it has read in that page. And so now if I go to examine 0 and I look at the contents, it's got, you know, some usable code in here. This is a little loop that basically counts, and the speed is controllable by the user input switches. So if I go to location 0 and say run, you can see I'm counting in binary here, counting up. And by changing the value of the input port, I can change the speed at which this counts. So I can make it count faster. I can make it count at full speed, right? And I can slow it down, and so on. And so this is just some you know, sample code to play with. So let me go ahead and stop it. And let me start stepping this one instruction at a time. So I can do an uppercase S for an instruction step. And I can, you know, monitor my address down here. So I'm at address 3, address 2, address 3, address 2. I seem to be in some kind of loop. Okay. If I say bus sig, then as I step through my simulation, I will see what my bus signals are, basically the information that's available up here on these LEDs. So the value of M1, memory request, read, write, halt, and the current contents of the data bus. So if you don't have this in front of you, if you have it plugged into some peripheral device or something, right, we can still interact with it from here. I can also say bus all, and now I get extra information. As I step, I can actually see the contents of my registers, including the stack pointer and the program counter, and I get a disassembly of the current instruction, as well as the data bus and the regular memory and system signals. So now we can actually run this like, something we would do in GDB, where I can see I'm about to execute a decrement B instruction. I can see that B is equal to EA, and when I hit enter, it decrements to E9. And now we're going to say if it's not 0, jump to location 2. My status flags are AA. I'll break these out eventually in the command line interface. But that includes the not 0 flag. And so when I execute this, my PC will change from 3 back to 2, and we're going to decrement B again. So B is E8, and now it's E7 and E6, and so this is what my program is doing. We can also intervene. I can say let's set B equal to 2, and now when I step, decrementing B from a 2 will make it a 1, and when I step again, it will decrement to a 0, and this time my flags are 42 instead of A2, which means my 0 bit is set, and so the jump if not 0 will fall through, and my PC will change from location 3 to the next instruction, which is 6. And at location 6 we decrement A, which is currently 3, so that decrements to a 2, and that's not 0, so we go back and we do this all again. We start decrementing B, and so on and so forth. So I can set B to a 2, I can set A to a 1, and I can step, and A is a 1, B is a 2, gets decremented to 1, jumps back, decrement B again, jump if not 0, well it'll fall through that to location 6. This is going to decrement A, so now A is a 0, my flag is 42, so the 0 bit is set. If it's not 0, it'll jump back, but it's going to fall through and it's going to go to a PC of A, and here it's going to load the current C register into the A register. And C is currently set to 3C, so I don't know, let's set C to 55, and let's step that. So it loaded C, which was 55, into A, and now it's going to send that to the output byte. So the output byte is right here, so when I execute this instruction, my output changes to 55, right? The good old alternating 1-0 pattern. And now it's going to increment C for the next time we do this. So C changes to 56, we go back to location 0, and we do this again. So we can play these debugging games now, right? And we can monitor what's happening, and we can manipulate what's happening. And I'm doing this at the instruction level, but we can also do this at the M cycle level. But if you are in between an M1 cycle, your prompt will change to a question mark, which tells you, if you want to look at your registers or change them or examine memory at some location, you can do that, but you're going to disturb the state of the machine. The AT328 has no direct access to the registers inside the Z80, obviously. Those things are, inside the silicon of that chip. But what the processor is doing is taking over control of that Z80 temporarily, zombifying it in some sense, and saying, hey, take your A register and push that onto the stack. And then instead of letting it push it onto the stack, it monitors the memory buses and sees what value is being pushed onto the stack. And it says, oh, interesting, you pushed a 04 onto the stack. I guess that's the value of A. And then it asks it to pop from the stack in order to undo that push operation. And so it does these things in a way that doesn't disturb the flags or the program counter or any of the other registers. But by doing these kinds of things, by executing different instructions, it can deduce the value of these registers, the program counter, and it can look at the contents of that location in memory and the subsequent locations to decode this instruction. This does not work if you're in the middle of executing an instruction. Right now the CPU is getting ready to do a memory request. It's trying to read an operand, and if I change what's on the bus, right, that's going to disturb it. So the question mark means basically interfere with the CPU at your own risk. So I can step through until it finishes. You know, it's fetched the low byte of a jump address. It's just fetched the high byte of a jump address. And now it's executed the jump. It's back to location 2. My prompt is a greater than sign. I'm allowed to tinker with the bus at this point. So we can do that, and we can also, you know, single step our way through one clock cycle at a time. And there you've got 10 instructions, 10 clock ticks for the jump instruction. We've got 4 for the decrement. Here comes another 10 for the jump. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we're back to the decrement. So you can do a lot of analysis of the system and the clocking and the whole operation of it like this by controlling the ticking and looking at the bus signals and so on. So we can set the register values. We can also just look at the registers anytime we want by saying regs. Again, as long as we understand that, you know, this might upset the state of the CPU. Writing and reading files, we can do a reset operation, which will do, you know, the same thing as hitting the reset button. And that's pretty much it. So there's a few more bells and whistles I might put in here. But there's also one other hidden command in here, which is the ability to load binary code into the memory of this machine. So for example, right now if I look at location 100, it's gibberish, right? It's got a reset instruction and a set bit 5 and stuff like that. There's nothing in particular in here. Suppose I want to write some code and load it into the system without going through the front panel. Now the front panel interface is fun. It's a nice way to, you know, really get kind of, you know, hands-on with the system and load in a program. But eventually, you know, you want to write larger programs. You don't really want to do that. You want some way to load things in more conveniently. So let me kick out of here. So I'll just Control T and quit. And there's a number of tools out there for doing Z80 assembly. So I'm using one called Z80 ASM, and this is, you know, freely available, open source. It's written by Brainsoft, and I don't know how to pronounce this person's name, but Achim Flamenkamp, I don't know, sorry. But they've done a beautiful job of writing this full-blown assembler that also includes an emulator. So I'm mainly using it for the assembly part, and I can do something like this. I can make assembly language code. So here's some code for reading in the value of 4 bits from the low and high nibble of our input port. So I'm going to read in from port FF into A. I'm going to save it in B, and I'm going to start doing some bit manipulations to pull off the low 4 bits, put that in the number C, and then take that number, rotate it right 4 times, take the low 4 bits of that, and put that into B. And then I'm going to add those 2 numbers together and send the result to my FF register, which is my output port. So this is a simple program that will add 2 4-bit numbers repeatedly and display it on the output port. Okay. Now, right now, you know, if I reset and I run my system, it's doing my counting program, right? So these switches just control the speed at which I count. So what I want to do is I want to take this code, I want to assemble it, and I want to dump the assembly language, the assembled code into my processor. So Z80 ASM, I'm going to ask for a listing, and I'm going to do add.asm and send the output to add.bin. So there's the assembly language listing. It's 22 bytes, and I can see my machine code DBFF473E0F and so on. And this creates a binary file. And if I look at the contents of that file, I see an 8-byte header, so Z80 ASM followed by Control Z in a new line. And then I see a starting address, and then the binary bytes of my file, dbff473e and so on. That's this data up here. So it's a very straightforward format, no real parsing required. And what we'd like to do is take this binary data and load it into the Z80 starting at this address. So there's a Java program I've created. I just call it loader, and this will be on GitLab as well. And if I run that, I pop up a window which shows me all of my possible ports that I could connect to. So port S4, I don't know what that is. It's always there. It doesn't do anything. The port I'm looking for is the FIDI port. Okay, this is port 1. When you put this on Wi-Fi, and the next version will have an ESP1 over here, so it'll be Wi-Fi enabled. You can also use this to connect to the Wi-Fi port, which is port 8081 at the 88 address. But I'm just going to use port 1, which is the FIDI, so I'll say open, and it tells me it's opening the USB UART, and I get this similar window, right? It's my terminal I/O program, basically, that I can, do basic commands. But the other thing that this loader lets you do is it lets you transfer binary data. So I can say choose file. I can come into Z80 and Z80 work, and there's my add.bin. And it tells me it's opened that for reading. And if I hit the load button, you'll see the lights on here flash really briefly, because this is only 22 bytes. And then you'll get a completion signal from the data bus. So it loads in, there's our completion signal, and it tells me it loaded 22 bytes. And now if I look at location 0, and I disassemble that, right, there's the bytes of my add program. Right, so I was reading from port F and masking and saving, and then reading again and rotating and adding them together and sending them to my output port. So we can write assembly language code, we can assemble it, and then we can dump that binary file into here just by saying, load that file, and it will send it through. And basically there's an undocumented command in here called uppercase L, and when you put this in the mode by typing in uppercase L, it will receive bytes in hex and load them into consecutive memory locations and send back an ACK periodically until you send it an invalid hex character, and then it exits. So it's a pretty straightforward protocol. And now, I can go back, I can say reset, and I can run, and this is adding. So right now it's adding 0 and 0. If I flip one of these to a 1, it's adding 0 and 1 is 1. If I flip this bit, this will do 1 plus 1, and that's a 2. And if I want to do 2 plus 2, well, there's 2 plus 1 is 3, 2 plus 0, but 2 plus 2 is equal to 4. And so we can crank them all up and add 15 plus 15, and that's 30, right? 1 bit shy of 31. So the ability to do some degree of more involved development. Now, I still primarily imagine this as a learning tool for working at the assembly language level, the machine language level, working with the front panel, and so on and so forth. But if you want to do something more serious, right, you can develop assembly language code, dump it in, and remember, you have the ability to save stuff in the flash memory. So I could say, let's save all of this from page 0 to page 1. Let's save this in file register 2. So I can load in a 2, I can say start at page 0, end at page 1, and now if I say stop examine, it will go ahead and it will copy this program into my static RAM. And so now if I power off, and I can unplug, so it's completely detached, power it back on. Now if I want to read from that file, I can say stop deposit, and it will load that value in, and now I've got, well, I have to reset and run. Now I've got my add program back. So we can do 2 plus 2 equals 4. There's 2 plus 2 equals 4. And if I come back here and I read from file register, oh, I just overwrote my file register one. Well, anyway, so that's file register one now. So anyway, that's some of what we can do with the command line interface. I'm still adding options to it, but you know, the new version of this board is going to have headers over here for accessing all of the address data and memory and control signals from the Z80. So theoretically, we can hook this up to other devices and, you know, get out of the box. And then you might want to start putting in you know, more serious code, and you have that option using these kinds of tools. All right, that's all I got. Thanks. Talk to you later. Bye.